Okay, so in this section we're going to be exploring absolute value equations and inequalities. So here I have the absolute value of x equals 3. Now let's take a look at what that really means. It's basically saying that we're moving a distance of 3 units from, let's say, 0. And it's going to be either 3 units this way, or since we're talking about just distance, we're not assigning any sign, 3 units this way. So therefore, x could have a value of positive 3, or x could have a value of negative 3. So we can condense that to say x is plus or minus 3. So if I had something like x plus 2 equals 3, what we're saying now is that we're actually going to be shifting where the center is. So if you remember when we talked about parent functions, the inside term, the h, if you will, is going to move you horizontally. This works kind of the same way. Now we're only dealing with one variable here, just the x, but that's why we only have one axis, an x-axis. If there was a y, we'd throw in the y-axis. Now the plus 2 simply indicates to us that we'll be starting here at negative 2. So it's kind of like, it's working backwards like we did with the horizontal shifting in our parent functions. And so we would be starting here, and then we're moving a distance of 3 in either direction. So we could be moving 3 to the right, which would be 1, 2, 3, and that would leave us at positive 1, or we could be moving 3 distance here, 3 units this way, which would leave us at negative 5. So in this case, we could see that x could either be 1 or x could be negative 5. Let's take a look how that might be done algebraically. So I'm just going to take the same problem here, and I'm going to take off the absolute value sign. So the absolute value sign, as you remember, makes everything positive. So if I have an x plus 2 equals 3, I could also, because we were moving that absolute value sign, it could be a negative 3 as well. And then we're going to solve these independently. So this one we would just subtract 2 from either side, and x could equal 1. And we'd subtract 2 from either side here, and we'd see that x is equal to negative 5. And so here we get the same values, but we just solved it algebraically as opposed to having to use a number line. The way we'd write that solution is x is equal to, and then we'd use the set notation, negative 5 and 1, and we would box that in like so. In our second example, I noticed that we have a term here in front of the x, a 4, and then we're doing the plus 12 equals 28. So now since we have a coefficient on x, it becomes a little more confusing as far as how does that work exactly on a number line. So we'll rely strictly on the algebraic method because that's a lot easier to work with at this point. 4x plus 12 is equal to 28, and since we moved the absolute value sign, we're also going to have to put the negative version. We have to change the sign, equals negative 28. Okay, now and then we just start solving these independently. So I'm going to subtract 12. So 4x is equal to 16. Divide by 4, and x is equal to 4. And this side I'm going to subtract 12. And then we're left with 4x is equal to, and that's going to give us 40. Divide by 4, x is equal to, well, that's going to be negative 40. So therefore x is going to equal negative 10. So we have two values. X is equal to negative 10 and 4. I just list them from the smallest value to the greatest value, and then we'll box that answer in like so. That's a much cleaner box right there. Now, this example, notice that we have a 4x on the left in the absolute value signs, but we also have an additional x term right here in the 6x. So solving this one, we're going to take the same approach, but there's something we have to be a little careful of. So let's go ahead and start, and I'll show you what you have to be careful of. So 4x plus 10 is equal to 6x, and 4x plus 10 is equal to negative 6x. So I'm going to subtract 4x from either side. Let me actually show that. Let me clean this up a bit. And we're left with 10 is equal to 2x, divide by 2, and x is equal to 5. Okay, on this side, I'm going to go ahead and subtract the 4x. So we'll cancel here and here. And 10 is equal to negative 10x, divide by negative 10. And we're left with an x value of negative 1, like so. So x is equal to negative 1 and 5. Okay, now here's what you have to be careful of. You really should be checking your answers, and there's a good reason for that. It's not just to see are you right, but in order to get the right answer, period, you need to substitute both of these values in. So let's do that. Let's see what happens. So I'm going to start with by substituting the 5 in. Okay. Now, let me get a little more room here. We'll evaluate that, and let's see, we have 20 plus 10. So the absolute value of 20 plus 10 should equal 30, and indeed it does. 20 plus 10 is the absolute value of 30, and the absolute value of 30 is 30. Okay, so that checks out. All right, let's try the other term, which was negative 1. So we'll say the absolute value of 4 times negative 1 plus 10 is equal to 6 times negative 1. So I evaluate the left side here, so that's going to give me 4 times negative 1 is negative 4, plus 10 is equal to negative 6, and we're left with the absolute value of 6 is equal to negative 6. And then we see here that, oh, well, the absolute value of 6 is 6, and that's equal to -6, which is not true. This is not equal. So we actually have a solution that doesn't really work. So here's how we write that. So 5 worked. So we'll say that x is equal to 5, and that's our solution, but we're also going to state that x equals -1 is an extraneous solution. Okay? And I'll box that in separately. So it's not really a solution that works for our problem. So we have to be careful of these extraneous solutions. And the only way that we can find them is if we substitute them in and see if we get a true statement. So you have to be on the lookout of those. Usually those are going to show up when you have an x on either side of the equal sign. Alright, so now let's look at inequalities and how to work those. So here I have 3x, absolute value of 3x minus 7 is greater than or equal to 5. Now we'll solve this just like any other inequality, except that we're going to have to break it up on either side, left side and right side, where we have, what I mean by that is we're going to have a positive 5. So just like with the equations, we're going to have to change the value of the 5 to a positive 5, and then we're going to have one where it's going to be a -5. But remember, I just changed the sign on the -5. That's like multiplying by a -1 on the right side. So that means we have to change the inequality sign. We're going to have to flip that around in order to maintain a true statement. Okay, so now let's go ahead and work the one on the left with the positive 5. 3x is greater than or equal to 12. And divide by 3. And x is greater than or equal to 4. Okay, now this side. 3x is less than or equal to, actually let me show my work, I'm being bad about that, 2. And then I'm going to divide by 3, like so, and x is less than or equal to 2/3. Okay, now I'm not done with how I'm going to write my answer, but I am going to graph it, and then I'll write my final answer, and I'll show you what I mean. So you'll be expected to graph, and we'll start off with plotting down our points. Since both of these have like an inequality with an equal to part to it, an inclusive inequality, if you will, then we're going to place a point at each spot. So here at 4, and then another one at 2/3. Now, you can't just place it, right in the middle between 0 and 1. It's actually going to be closer to the 1. It's going to be 2/3 the distance to 1 from 0. Okay, so we have our points. Now let's think about what this is saying. This one is saying x is greater than or equal to 4. Well, greater than tells me that it's going to be the values that are going from here to here. If I were to look at the other one, I can see that x is less than or equal to 2/3. So from there, I'm going to go less than. in this direction. Now, see how the arrows are facing? So if you recall when we were talking about graphing inequalities, this is indicative of an OR statement. So here's how we write our final answer. We're going to state that x is less than or equal to 2/3, or x could be any value greater than or equal to 4. And those values will work when you substitute them into the inequality. Don't worry about extraneous solutions when dealing with the inequalities. I'm not going to throw any extraneous solutions in the inequalities at you in your assignment. Okay, so these are basically there's a pattern to this. If you graph them over and over and over again, you'll notice that any inequality that is either less than or equal to, you're going to have an AND statement, like so. And as you remember, AND statements are graphed with similar to a line segment. And then if we were to look at the greater than or equal to, we would end up getting an OR statement. And those would be like opposing rays. So make sure you write that down. You really don't need to necessarily memorize this, because you can figure it out, just like we did with that previous example. Alright, so let's look at an application problem, a real life problem, if you will. So in this example 5, Frito-Lay lists the weight of their chips on the packaging. If you were to weigh the bag, you would find that it did not exactly match what was listed on the packaging. They allow for a tolerance of 3 ounces. So that might be, you might get an extra chip and it might be 3 ounces over, or you might be short a chip and it might be 0.3 ounces less than that. So what are the maximum and minimum, aka the extreme values or weights, the amounts the chips can weigh for quality control to allow them to ship to market? So we'll need to figure out what do we know, what do we need to figure out. Well, one of the things that I know for sure is we have this tolerance of 0.3 ounces, okay? And if you actually look at the bag here, and we're going to actually need to know what that ideal weight is, what they're shooting for. And so if we look at the bag and zoom in on here, I can see that it's 2 3/4 ounces. All right, so basically we're going to go a little bit above that or a little bit below that. We have the ideal amount, and if we subtract the actual amount that we have from the ideal amount, then we'll get the tolerance. So let's go ahead and define our variables with our let statement, and we'll say let, and then we'll say, go ahead and just use x equal the extremes, okay, meaning the maximum and minimum weights. And then we're going to go ahead and set up our inequality. So basically the ideal weight is 2.75 ounces, as we see here on the package. If we were to subtract out the extreme, that difference should be within 0.3 ounces. Okay? And it can't be any more than that. So the difference between your ideal weight and what it actually weighs. And I can probably clarify that by saying this is the actual weight. All right, so we'll just go ahead and solve this. We'll get 2.75 minus x equals 0.3, and 2.75 minus x equals negative 0.3. So let's see, I'm going to subtract 2.75 from either side, leaving me, since it's minus x, I'm going to leave the negative with the x. Okay, and let's see, that's going to be negative 2.45. And then we're going to divide both sides by -1, so x is going to equal 2.45. And then we'll do the same thing on this side. We'll solve this one out. So I'm going to subtract 2.75. Negative x is equal to 3.05, negative 3.05. Therefore, x is equal to 3.05 ounces. So, we have our values for x. Since there's more than one answer, I'm going to use set notation. 2.45 and 3.05. And then we're going to write our therefore statement. So therefore is 3.05 ounces. And that would be our solution. So I box that in.